Hello, and thank you for tuning in. Let's start with a simple reality. Many engineering teams encounter a unique challenge once a system reaches production maturity. Is our working product architecturally sound? Are there operational risks hidden beneath the surface? To answer how to tackle this, we'll be showcasing a structured software design analysis for a fully implemented AI-powered smart assistant for debt collection agents. This analysis across 4 phases: architecture, risk, implementation, and failure simulation with the goal of validating system design. Let's start with architecture analysis. In this phase, the question we want to answer is if our current system actually supports the requirements it claims to, and is the overall architecture reliable? The answer is yes. Let me show you why. This is the requirement for AI Smart Assistant. This is the prompt used. The Smart Assistant is a modular monolith on FastAPI with single deployable, logically separated internals. It answers 4 questions per customer: who to call, how to reach them, when to reach them, and what to say. One crucial decision here is rule-based channel preference and time inference. Deterministic, reproducible, zero LLM cost. AI is used only where reasoning adds value: priority enrichment, talking points, and message generation through Vertex AI Gemini with centralized logging. For route groups, cover the full surface: sync, scoring, channel analysis, and message generation. Storage is file-based JSON with cache aside at every layer. Module structure is cleanly separated across routes, services, models, prompts, utils, config. The final analysis is that our overall architecture is requirement complete, consistent, and answers all 4 business questions, mapping directly to endpoints and services without gaps or orphan components. The next phase of our analysis is risk validation. This phase answers, what could realistically go wrong in production, and do we have visibility into each scenario? Upon checking, we identified 7 operational risks, 3 high, 4 medium. None blocking, but there were 3 require active awareness. This is the prompt used. First, if Vertex AI goes down, scoring degrades and messages fail hard on a cache miss, and the agent gets an error. Second, all persistence lives on local disk, so ephemeral containers means a redeploy wipes all cached states, forcing cold start recomputation for every user. Last, priority scoring invokes the LLM sequentially per customer with no timeout, increasing blockout times. On the medium side, we found no file locking for concurrent writes, credential expiry invisible to health checks, linear sync file scans, and no payload size limits on ingestion. All understood trade-offs within the current single-instance deployment model. Our next phase was implementation design. This phase had to answer, how is the system actually built? What does the API look like, and does implementation match documentation? Thankfully, it does. Let me walk through the API surface, then the runtime behind it. This is the prompt used. The system exposes 17 REST endpoints across 5 route groups: customer sync for ingestion, agent actions for scoring and suggestions, communication analysis with a stateless 0 LLM channel ranker, message generation for compliant scripts and emails, and a health endpoint. Together, they cover the complete lifecycle: ingestion, scoring, analysis, generation, and cache management. Runtime is fully synchronous. Each request completes in a single call stack. Priority scoring calculates base scores, enriches via Gemini, sorts by date, caches, and returns only on miss or refresh. Message generation follows the same cache-first pattern. Deployed on render with Docker, compliance embedded in prompt templates, authentication handled upstream. Implementation is fully consistent with documentation. API surface is complete, all 4 business questions served with CRUD, caching, invalidation, and stateless analysis support. Patterns uniform. System operates as a coherent unit. Last, we simulate failures to answer, does the system degrade gracefully or cascade? Thankfully, scoring degrades gracefully. Message generation fails hard on LLM outage, but only on cache miss. This is the prompt used. We simulated 8 failure scenarios. When the LLM goes down, scoring degrades partially through defensive isolation, but messages fail hard on cache miss. Large roster cold starts scale linearly with no cap. Concurrent refreshes duplicate fully, double LLM cost, potential file race. Invalid responses are caught by fault isolation and post-generation validation. File write failures lose computation, next request starts over. Overall, the system degrades without cascading. It doesn't self-heal, but it doesn't collapse either. We found that the system recovers partially from all simulated failures. No cascading catastrophic scenarios. Scoring is resilient by design. Message generation is binary, works or errors. This was acceptable for current scope. So, what's the overall outcome? We validated a production-deployed system across 4 phases: architecture, risk, implementation, and failure simulation. The architecture is requirement complete. Every business question has a dedicated endpoint, backing service, and caching layer. Workflows are consistent end-to-end. Risk level is moderate. LLM dependency, file persistence, and synchronous scaling, all understood trade-offs for the current model. Infrastructure is minimal. Caching keeps LLM costs effectively free on repeat calls. Rollback is a simple container redeploy with zero data impact. Our finding was that the assistant was suitable for continued production operation. The system combines deterministic reliability where cost matters with AI where reasoning adds value. Implementation confidence is high. The system is production-worthy. At ByteRich, we're proud to help our customers turn their vision into reality. Thank you.